What's up, everybody? We are starting chemistry session 4. We're on page 37. Only 1,300 more pages to go. We're going to start with a chemistry in everyday life. You may have seen the symbol shown in figure 1.21 on containers of chemicals in a laboratory or workplace, sometimes called a fire diamond or hazard diamond. This chemical hazard diamond provides valuable information that briefly summarizes the various dangers of which to be aware when working with a particular substance. So we got the bottom the bottom diamond that shows specific hazards: oxidizer, acid, alkali, corrosive, use no water, radioactive. The reactivity may detonate, shock and heat may detonate, violent chemical change, unstable if heated, stable. Okay, we have a health hazard. Number 4 is deadly, extreme danger, hazardous, slightly hazardous, or normal material. Then we have flash points. 4 is below 73 degrees Fahrenheit. 3 is below 100 degrees Fahrenheit. 2 is above 100 degrees Fahrenheit, not exceeding 200 degrees Fahrenheit. 1 is above 200 degrees Fahrenheit. 0 is will not burn. Okay? So pretty straightforward. The National Fire Protection Agency, Nfpa 704 hazard identification system was developed by the Nfpa to provide safety information about certain substances. The system details flammability, reactivity, health, and other hazards. Within the overall diamond symbol, the top red diamond specifies the level of fire hazard, temperature range for flash point. The blue left diamond indicates the level of health hazard. The yellow right diamond describes reactivity hazards, such as how readily the substance will undergo detonation or a violent chemical change. The white bottom diamond points out specific hazards, such as if it is an oxidizer, which allows the substance to burn in the absence of air or oxygen, undergoes an unusual or dangerous reaction with water, is corrosive, acidic, alkaline, a biological hazard, radioactive, and so on. Each hazard is rated on a scale from 0 to 4, with 0 being no hazard and 4 being extremely hazardous. Alright, 1 second. What was I going to do? Oh, checking my volume. Sound control panel. So it's recording, microphone, properties. It's all the way up. Okay. Alright. While many elements differ dramatically in their chemical and physical properties, some elements have similar properties. We can identify sets of elements that exhibit common behaviors. For example, many elements conduct heat and electricity well, whereas others are poor conductors. These properties can be used to sort the elements into 3 classes: metals, elements that conduct well; nonmetals, elements that conduct poorly; and metalloids, elements that have properties of both metals and nonmetals. The periodic table is a table of elements that places elements with similar properties close together. You will learn more about the periodic table as you continue your study of chemistry. Yay! Alright. Similar properties close together. That's the periodic table. And memorized. 1.4 Measurements. By the end of this section, you will be able to explain the process of measurement, identify the three basic parts of a quantity, describe the properties and units of length, mass, volume, density, temperature, and time, perform basic unit calculations and conversions in the metric and other unit systems. Yeah, let's hope. Measurements provide the macroscopic information that is the basis of most of these hypotheses, theories, and laws that describe the behavior of matter and energy in both the macroscopic and microscopic domains of chemistry. Every measurement provides three kinds of information: the size or magnitude of the measurement, a number, a standard of comparison for the measurement, and an indication of the uncertainty of the measurement. While the number and the unit are explicitly represented when a quantity is written, the uncertainty is an aspect of the measurement result that is more implicitly represented and will be discussed later. The number in the measurement can be represented in different ways, including decimal form and scientific notation. Alright. Science Daily break. Let's break for the Science Daily. Alright, so what we got in top science news? We have History of the Crusades, told by Crusaders' DNA. Fossils found in museum drawer, huge carnivore. Gene therapy restores immunity in infants. Saw that last time. Functions in pig's brain, restored hours. I read that one. Okay. Top health. How blindness shapes sound processing. CRISPR treats lung disease before birth. Decline in measles vaccination. Resurgence. Antibody suppresses HIV for up to 4 months. Top physical tech. Quantum gas turns supersolid. Defying the laws of physics, bubbles of sand. Snake-inspired robot slithers fast. Cooling without energy consumption. Let's check that out. Thermodynamic magic enables cooling without energy consumption. Physicists have developed an amazingly simple device that allows heat to flow temporarily from a cold to a warm object without an external power supply. Intriguingly, the process initially appears to contradict the fundamental laws. Let's check that out. Maybe we'll all get free air conditioning. Fundamental laws of physics. Physicists at that university have developed an amazingly simple device that allows heat to flow temporarily from a cold to a warm object without an external power supply. Intriguingly, the process initially appears to contradict the fundamental laws of physics. If you put a teapot of boiling water on the kitchen table, it will gradually cool down. However, its temperature is not expected to fall below that of the table. It is precisely this everyday experience that illustrates one of the fundamental laws of physics, the second law of thermodynamics, which states that the entropy of a closed natural system must increase over time. Let's see what entropy means. Entropy. A thermodynamic quantity representing the unavailability of a system's thermal energy for conversion into mechanical work, often interpreted as the degree of disorder or randomness in the system. Lack of order or predictability, gradual decline in disorder. Or more simply put, heat can flow by itself only from a warmer to a colder object. From a warmer to a colder object, and not the other way around. Cooling below room temperature. The results of a recent experiment carried out by the research group of that guy in that department at that university appears at first sight to challenge the second law of thermodynamics. The researcher managed to cool a 9-gram piece of copper from over 100 degrees Celsius to significantly below room temperature without an external power supply. Theoretically, this experimental device could turn boiling water to ice without using any energy, says Schilling. Creating oscillating heat currents. To achieve this, the researcher used a Peltier element, a component commonly used, for example, to cool minibars in hotel rooms. These elements can transform electric currents into temperature differences. The researchers had already used this type of element in previous experiments in connection with an electric inductor to create an oscillating heat current in which the flow of heat between two bodies perpetually changed direction. In this scenario, heat also temporarily flows from a colder to a warmer object so that the colder object is cooled down further. This kind of thermal oscillating current circuit Hello? Hey. back to it. Alright. Should be right here. This kind of thermal oscillating circuit in effect contains a thermal inductor. It functions in the same way as an electrical oscillating circuit in which the voltage oscillates with a constantly changing sign. Laws of physics remain intact. Until now, Schilling's team had only operated these thermal oscillating circuits using an energy source. The researchers have now shown for the first time that this kind of thermal oscillating circuit can also be operated passively, i.e., with no external power supply. The thermal oscillation still occurred, and after a while, heat flowed directly from the colder copper to a warmer heat bath. With a temperature of 22 degrees Celsius without being temporarily transformed into another form of energy. Despite this, the authors were also able to show that the process does not actually contradict any laws of physics. To prove it, they considered the change in entropy of the whole system and showed that it increased with time fully in accordance with the second law of thermodynamics. Potential application still a long way off. Well, that sucks. Although the team recorded a difference of only about 2 degrees Celsius compared to the ambient temperature in the experiment, this was mainly due to the performance limitations of the commercial Peltier element used. According to Schilling, it would be possible in theory to achieve cooling of up to negative 47 degrees Celsius under the same conditions if the ideal Peltier element, yet to be invented, could be used. With this very simple technology, large amounts of hot solid, liquid, or gaseous material could be cooled to well below room temperature without any energy consumption. The passive thermal circuit could also be used as often as desired without the need to connect it to a power supply. However, Schilling admits that a large-scale application of the technique is still a long way off. One reason for this is that the Peltier elements currently available are not efficient enough. Furthermore, the current setup requires the use of superconducting inductors to minimize electrical losses. Okay. I was hoping for free air conditioning. Alright, let's look at chemistry. Defying the laws of physics. Bubbles of sand. Alright, let's get back to the chemistry. Scientific notation is also known as exponential notation. A review of this topic can be found in Appendix B. For example, the maximum takeoff weight of a Boeing 777-200ER airliner is 298,000 kilograms, which can also be written as 2.98 times 10 to the 5th kilogram. The mass of the average mosquito is about 0.000025 kilograms, which can be written as 2.5 times 10 to the negative 6 kilograms. Units such as liters, pounds, and centimeters are standard comparisons for measurements. When we buy a 2-liter bottle of a soft drink, we expect that volume of the drink was measured. So it is 2 times larger than the volume that everyone agrees to be 1 liter. The meat used to prepare a quarter-pound hamburger is measured so it weighs 1/4 as much as 1 pound. Without units, a number can be meaningless, confusing, or possibly life-threatening. Suppose a doctor prescribes phenobarbital to to control a patient's seizures and states a dosage of 100 without specifying units. Not only will this be confusing to the medical professional giving the dose, but the consequences can be dire. 100 milligrams given 3 times per day can be effective as an anticonvulsant. The single dose of 100 grams is more than 10 times the lethal amount. We usually report results of scientific measurements in SI units, an updated version of the metric system using the units listed in 1.2. Other units can be derived from these base units. The standards for these units are fixed by international agreement, and they are called the International System of Units, or SI units. From the French, Le Système International des Unités. SI units have been used by the United States National Institute of Standards and Technology since 1964. We got length, property measured length, name of unit, meter, symbol of unit, M. Mass, kilograms, mass, unit symbol, kilograms. Okay, sometimes we use units that are fractions or multiples of a base unit. Ice cream is sold in quarts, a familiar non-SI base unit, pints, or gallons, or quarts. Um, we also use fractions or multiples of units in the SI system, but these fractions or multiples are always powers of 10. Fractional or multiple SI units are named using a prefix and the name of the base unit. For example, a length of 100 meters is also called a kilometer, because the prefix kilo means 1,000, which is scientific notation, which in scientific notation is 10 to the third power. 1 kilometer equals 100 meters, or 1,000 meters equals 10 to the third, 10 to the power of 3 meters. The prefixes used and the powers to which 10 are raised are listed in table 1.3. Femto, negative 15, pico, negative 12, and nano, negative 9. And the rest of those. Alright, well, we're going to call it here. We're ending on page 41. Got through 4 pages. I know this is short, but I gotta do another live stream. Check me out on my Blender Lab. But alright guys, I'll see you later.